Worked together for decades. And so Jackie's a practicing scientist doing combustion research. She's at the Combustion Research Facility. And she's part of the Exascale project as well to do very large-scale simulations. And so it's my, there was one other piece, I gotta remember the other piece. Jackie got her PhD in mechanical engineering from Stanford University. And so it's my pleasure to introduce her, Jackie Chen.
I want to thank Jim and the organizers for giving me this opportunity to talk here, and I feel like a little bit of a fish out of water because you guys are all the experts, and I get to benefit from all of your work in terms of the analysis and visualization and trying to make sense out of the amounts of data that I generate. So the talk today is on analytics-inspired visualization. And we've been trying for a long time to generate a holistic workflow that includes both the solver part phase as well as the analysis of viz phase. And we're trying to move this process in situ, that is onto these large supercomputing machines, and doing this at extreme scale. So simulations are one source of large, massive data, others being from instruments, scientific instruments, from light source data, from telescopes, sensors, and other sources. But it presents, all of these large-scale data present a source of great challenges and opportunities for analytics and visualization. So shown here in this slide are a couple of large-scale simulations from the subsurface modeling community to molecular dynamics for looking at materials science and climate modeling and so on. The list goes on. And a lot of these really large simulations have been performed on these, for example, on the Department of Energy supercomputers, these capability machines located at Argonne and at Oak Ridge. This is the Mira and Titan machines. Titan will soon become Summit next year as we push on this towards an exascale machine, 10 to the 18 floating point operations per second. So I'd like to focus the talk today on just one of these science simulations dealing with combustion, which is my field of expertise. And so these are simulations that take a long time, a lot of CPU hours, hundreds of millions of CPU hours, and run on a significant fraction of these leadership class machines, on up to a couple 100,000 processors simultaneously. The holy grail in combustion that requires these massive amounts of computing is to be able to predict how new fuels in different combustion environments perform at the relevant conditions, that is at high pressure typically and under very turbulent conditions. And designers of practical combustors, the airplanes that you fly, cars and trucks that you drive to deliver goods, and the power plants that generate electricity in your homes and offices, require that we optimize both the design of fuels as well as the design of the combustors, or the engines, for example, with the overarching goal to reduce the amount of emissions, particularly greenhouse gas emissions, increase the efficiency so that we can responsibly use the remaining fossil fuel resources that we have, and more importantly, to shorten the time to market to make our industries competitive. So the methodology that I'll describe today is one of several combustion simulation methodologies. The one that requires the most intense computing and provides kind of the ground truth against which coarse-grained models can be compared is called direct numerical simulation. And its main use is to look at the very intricate couplings between turbulence and chemistry interactions as they occur under these relevant regimes to practical devices. And while the turbulence is fully spatially resolved, so there's no closure model for the turbulence down to the finest Kolmogorov scales where heat and mechanical energy are dissipated, there are still models that are incorporated for the chemistry and for transport, and there are uncertainties with these models. And so one area of research still, open research, is to look at how you propagate uncertainties in this rich thermochemical environment that's time-varying, has multi-scale information associated with the turbulence, maybe 4 decades of information. And these flows are typically very complex, so they're not your simple turbulence in a box, but rather they have deal with things like compression by a piston, opening valves, swirling flows in a gas turbine. They can come with multi-physics, with sprays, so you can have evaporating sprays or atomization of liquid fuels at the same time that you have reactions and soot forming and thermoradiation. So they're very complex flows with multi-physics. The code that we've developed over many decades is this code called S3D, developed in my research group at Sandia with support from the Office of Science and Department of Energy, VES. And the code is used to solve compressible reactive Navier-Stokes equations. It's a DNS code, and it uses very high order accurate methods, explicit 4th order in time using a method of lines, 8th order in space using a centered finite difference approach. And it has a very detailed multiphysics treatment, as I mentioned, for chemistry and for other spray and soot physics. The code has been refactored a number of times, starting from an MPI code to a OpenACC code with pragmas so that it can run effectively on GPUs, to the most recent refactorization in a asynchronous task-based system called Legion, which is one of many asynchronous task-based data-centric models that are programming models that are out there. And we've incorporated, with the help of this community, a lot of the in-situ analysis and visualization tools. The resulting data that we generate is very large, can be upwards of, per run, upwards of several hundred terabytes to about a petabyte, which is our largest data to date. And because of the sheer size of it, we can't save all of the data. So we typically drop out restart files maybe every 400, 500 time steps. And that allows us to not only checkpoint restart, but also lets us do post hoc analysis with the data. In addition to the field data, which could be 100 different fields representing the range of chemical species that we transport, we also have about 50 terabytes of particle data that we generate. Particle data are useful for aggregating Lagrangian statistics, especially in situations where you have intermittent phenomena like localized quenching of the flame or local pockets where a mixture is auto-igniting. So you'd like to actually sit on the fluid parcel and traverse that in time and space and aggregate statistics in a Lagrangian sense. The underlying turbulence where all this happens, all this physics happens, is chaotic. It's characterized by a wide range of scales, lots of rare events like the ones I mentioned, extinction, ignition, which you don't know when they're going to occur a priori. That's time-varying data, so it's 4D data, 3 spatial dimensions, 1 in time. And then we know that the turbulent fields that these reactions sit on are sitting in organized, coherent motions. And so we don't want just point-wise statistics, but there's spatial information that would be lost. And so we're interested in non-local behavior and structural information and causality information between the scalar fields and the vector fields. The vector fields being the velocity, entropy, strain rates from the turbulence. And this is all tightly coupled. Oops. So the current workflow of, that we've been used to for decades is to compute first, analyze post hoc later, is having a very difficult time scaling even on today's petascale machines, let alone pushing towards the exascale. And this is because of the ever-increasing gap between compute throughput and the available I/O rates. So it's difficult to save sufficient data for post-processing. The computing centers don't want to buy huge disk farms, which is expensive. And we don't save them at a sufficiently high temporal frequency now in order for us to capture these rare events that oftentimes have catastrophic effects on macroscopic quantities like efficiency or emissions or safety. So we would like to be able to integrate analysis in situ together with the solve. As I said, this is driven somewhat by the constraints of machine architectures and the direction those are headed. So this is a image of what a conceptual node on a future exascale machine might look like. It has a great deal of heterogeneity in terms of the architecture, with lots of CPUs, cores, and accelerators, and all kinds of memory, DRAM, and then even non-volatile RAM, and burst buffers where you can provide local node storage. And because of the cost of power that's prohibitive, the currency is changing quickly from floating points operations are free to where data movement dominates the entire cost. And so with this paradigm, you want to minimize the data motion both within the node as well as across the interconnect across the entire machine. And so that forces us, and then there's tons of concurrency achieved by exponential growth and parallelism within the chips. Maybe we're talking about millions of cores, and lots of latencies all throughout this entire machine between the memory, different layers of memory, the latencies out to the disks for I/O, and latencies across the network. And so the holy grail here as we move forward is to express data locality and independence, to be able to reason about the dependencies of different parts of your software, express massive parallelism, and to minimize any kind of global synchronizations and reduce data movement. So that can be all said for creating the solver first, but it can also be said for multi-physics modules. That also applies to analysis and visualization modules if you want to, or libraries, if you want to include that into an in-situ workflow. And so that brings up that we have a very, very rich design space in order to have a efficient working holistic workflow. And this design space also critically impacts the analysis and visualization algorithms and how they are structured. And the design space of these workflows and some of the considerations that have to be thought about are where are you going to locate analysis compute resources? Are they going to be located on the same compute cores, on dedicated cores on the same node of the machine, or shipped off to a secondary staging area, or possibly even off to disk for post hoc analysis? Those are some of the decisions that have to be made. And then you have to decide whether, which parts of memory you're going to use. Are you going to use handoff copy on DRAM on the same nodes, or are you going to use non-volatile RAM or disk? And you have to decide issues on whether you do the analysis in VIS in a bulk synchronous manner, or whether you do it asynchronously. For example, some parts of an analytics algorithm may not scale terribly well, and so maybe you want to ship those off to secondary resources on a given machine, where they don't impact the overall solver. And so depending on how you pick the workflow design, it also has very strong implications on how you write your analysis and visualization algorithms, whether they're written for in-situ purposes or in transit purposes, or in a hybrid sense, whether you're doing parts of your algorithm in situ, those that don't affect the solver and have a natural data decomposition, and then other parts of your algorithm that may cost a lot more in terms of time or memory could be shipped off in transit. So some of the considerations in exploring this design space for in-situ workflows is that you want to minimize the performance impact to a large-scale simulation. You obviously don't want to have all of your time in the analysis phase and not be able to actually finish the computation. So you need to work within the time and memory constraints of a large-scale simulation, and you also don't want to pollute cache, so you want to have minimum impact on cache if you're sharing memory resources with the solver. We also know that there's a wide range of arithmetic instructions characterizing the different solvers as well as the different analysis algorithms. And they have very, very different data dependencies, different communication patterns. They scale, some algorithms scale better than others. And some instruction mixes are floating point rich and others have no floating point operations and are rich in branching operations and integer operations. And so this is a very challenging space to have to design for. So in the combustion field, we're very much interested in multivariate volume and particle rendering. These are some of the algorithms. And particle query, we want to query both the field data as well as the particle data. We are interested in feature detection, segmentation, and tracking using topological methods. And some of the representations of the topology are, from a mathematics standpoint, are things like contour trees, Morse mail complexes, time tracking in a graph, and comparing scalar fields. We need to filter and average the data. Oftentimes we're interested in the underlying coherent turbulent motion, so we're interested in the shape or geometry analysis, and how long is a given mixing rate structure compared to the underlying turbulence structure that's causing the mixing of two chemical species. And then, of course, we're interested in statistical moments and UQ-driven sensitivity analytics, using some of the feature selection to guide localized quantities of interest. I should just reemphasize that the arithmetic mix for these different types of analysis vary greatly. For example, the topological methods typically build large graphs. They include a large number of integer operations and no floating point operations, and are highly data dependent depending on the size of your features. On the other hand, computing statistics is floating point rich, it's compute intensive, and it's naturally data parallel, and so you can probably put a lot of that type of statistical analysis, have it compute directly on the with the solver in a bulk synchronous manner. It also has very low communication, except for perhaps the aggregation stages of the statistics. So let me go through a few case studies in combustion that use and need this in-situ framework. The first one has to do with identifying, classifying, and tracking some of these complex intermittent features and their statistics. So for example, in combustion, we're concerned about localized extinction, that is where the flame goes out when the strain rate or the turbulence is too intense. And if that extinction, localized pockets of extinction is pervasive, then you can have blowout and your, for example, airplane would stall, which would be very undesirable. So you're concerned about design spaces of how you design the fuel mixture, how you design the strain, the turbulence environment that it has to operate in, and so on. And so it's useful here to have a tool to do this feature detection tracking. To do this in a rigorous sense, we've borrowed on tools from combinatorial topology to help us locate these features, especially in scalar data and more recently vector field data. And with these methods, critical points are identified combinatorially. Some of these critical points shown here in one dimension, 2 dimensions, and 3 dimensions involve things like local minima, maxima, and saddle points. And overall, what we're trying to do is to look at data structures that can be represented by contour trees or merge trees, Morse mail complexes that look at the gradient features of a scalar, and Jacobi sets that help us track features in time. So let me show you one example of localized extinction followed by reignition in a turbulent jet flame simulation. Initially in the movie, before I play it, you're going to see the flame mixture fraction and the stoichiometric mixture fraction where the flame exists. Then on the left, what you will see in the animation is the OH radical, where red is high values of burning and blue is quenched localized extinguished regions. Then there will be a plan view, top view, red is burning, blue is extinguished, and on the right are the corresponding localized mixing rates, or what we call scalar dissipation rates, where pink coincides with these extinguished regions. Let me just play it real quickly one more time, because it went by kind of quick. So here's the flame, mixture fraction. The flame is shown by the white regions, the red is burning, blue are localized extinction pockets. And then we've taken a top view. See the holes, blue holes start to increase in size and complexity, and these holes seem to correlate very well with the localized mixing rate or scalar dissipation rate. So the question for us is how to understand this physics better. So we relied here on a topological abstraction. First, we rendered the data using volume rendering, the raw combustion data for the underlying mixture fraction field. And then we superimposed on that isosurfaces of these high mixing rate regions, or the so-called scalar dissipation rate. And this rendering was done on a massive data set of, like I said, a couple 100 terabytes. And we had to render this massive data set, we had to rely on multi-resolution visualization and streaming approaches using the VIS tool. In order to use that, we had to rewrite the output of S3D and write that out into an IDX format. But that multi-resolution viz allowed us to take variable resolution input files and then very quickly see or have a coarse grained resolution image of what was happening. And since this is time varying, we could start to look at the time varying behavior, and if we give it enough time, it would refine and come up with a more refined image. And so the method basically trades off the speed of reading and rendering and versus the accuracy of the images, given enough time. So from that rendering, we then applied the merge tree, contour tree methods to look at these localized level sets on a scalar field. And here we plot the, plot the scalar dissipation rate. These are the mixing rate structures superimposed on the flame sheet, which is shown in gray. And these were segmented using the contour merge trees. And these are the localized extinction regions that grow and change in time. And then we can track these features, these combustion mixing rate features, through this by looking at the spatial overlap of these level set components as they evolve in time. And this is concisely depicted in this tracking graph where time is this horizontal axis, and each of these blue lines represents one feature or component as it's tracked in time. These extinction pockets can form at any given time. They're birthed, or they can divide depending on the underlying local field, turbulence field. So they can split, or some of them can come together and merge, and some of them can reignite and therefore die. And so we have this rich range of features and their events that happen as they evolve in the turbulent flow. So from the feature graph, we can count at any given time the number of features. We can also measure the longevity of these features, and in some instances even get an idea of the size of the features as they grow in time and space. So it's a very powerful tool. And just to illustrate, this is a animation showing the mixture fraction the volume rendering, and the critical points, the local minima or maxima of these dissipation elements, high scalar dissipation rates, and we can then simplify the critical points and come up with just the underlying important localized mixing regions that are shown by the different colors. Let me play that really quick one more time. Here's the volume rendering of the mixture fraction. These are all the critical points that were identified. We can simplify the critical points in a concise representation, and then we can look at the regions surrounding the critical points, and these represent the local mixing structures that generated those extinction holes. So another example is a lifted flame stabilization problem, where we have a flame that is lifted typically off of a burner, like in your diesel engine. You have a fuel injection and the burner sits some distance downstream of the burner. So what happens in a diesel injection is you have ignition occurring, reactivity, you mix the fuel in the air, you evaporate it, and then you have reactions start to occur as the fuel and air ignite on its own. And then the lifted flame base is shown by the blue hydroxyl radical, sits on top of this soup of auto-ignition kernels. So what we're interested is to understand the stabilization mechanism. How does this lifted flame stabilize? Does it stabilize against the aerodynamic turbulence field that's coming at it? Or does it stabilize because of the help of these auto-ignition kernels? And so again, here we can use the similar segmentation approach to understand the complex relationships between the various scalar fields. In this case, we're interested in the flame surface is depicted by the red bits that are lifted off of the burner, which would be down here, flows going from bottom to top. The high scalar dissipation rate regions are the bluish structures, and you can see their spatial temporal relation with respect to the flame. And then these gold bits and pieces are the ignition kernels that are igniting upstream that perhaps interact with the flame base and the mixing field. And so we can encode their behavior again in this tracking graph. And this tracking graph clearly shows in time going from left to right. If we zoom in on it, you can look at several features. There's a red part of the graph which represents the lifted flame base turned on its side on the right part. And then these gold part of the graph are these ignition features. And so we can see upstream of when the ignition feature reaches the flame base, some of these ignition features split, some of them merge, and then eventually, here's an example of an ignition kernel that merges with the flame base. So you can really drill down and understand how these different scalar fields interact with one another. So another example, case study that we did was to look at turbulent auto ignition in a compression ignition engine. And this is a diesel jet. So experiments have very limited information. They have 2D planar information for some small set of species. They have time-resolved Schlieren images that allow you to look at density gradients. These are line-of-sight images, so they don't give you the instantaneous structure. But DNS has access to all of the detailed scalar and velocity field statistics. So in this case, we have a fuel slab in the middle, and ambient heated air on top and bottom, and it's a jet. So you end up with two auto-igniting jets at the interfaces between the air and the fuel. Let's see, let me jump here. And so what we were interested in is trying to understand the effects of molecular and turbulent transport in this two-stage ignition phenomenon. The first stage is where the fuel is broken down and it forms low-temperature radical soup, and then sequentially hot ignition occurs in some localized regions where the thermochemical conditions are correct, and it's bootstrapped off of the high temperature ignition is bootstrapped off of the low temperature ignition. So shown here in this plot of ignition delay time on the right versus mixture fraction. It's better. Ignition delay on the right on a log scale versus mixture fraction. That is the degree of mixing between the fuel and air, where 0 is pure oxidizer and 0.25 is pure fuel. What we see is that if you had no turbulence, so it's completely just homogeneously igniting, you first go through low temperature ignition here at very lean mixtures on the outer edges, lean mixtures where there's a lot of air and very little fuel. And then subsequently, because the ignition delay is longer, you then undergo hot ignition at a richer condition, maybe in the center part of the jet where the turbulence is high. But what we've discovered through simulation is that the parcels of fluid that ignite faster than where there's no mixing, the 0D case, are helped along by the low temperature ignition and its propagation into richer mixtures from the air side into the fuel side, and that creates the local thermochemical environment for high temperature ignition subsequently to occur. And so then overall, the discovery here is that hot ignition actually occurs, overall ignition occurs at shorter time and at richer conditions than predicted from homogeneous ignition. And this is also borne out a little bit in the experiments where you see low temperature ignition as you go in time. You see low temperature ignition occurring on the edges, and then subsequently the rich part of the flame all ignites, and then you get hot ignition occurring later. So an important message to take away is a lot of the information that scientists use is contained in the statistics. A lot of the physics don't occur because of in spatial dimensions, but occur in phase space. So in the combustion space, the ignition problem occurs where temperature and mixture fraction conditions are correct. So the evolution here is shown by just pure mixing of fuel and air. Subsequently, the temperature goes up a little bit on the lean side, and then the ignition propagates into the richer mixtures, and then you see high temperature ignition, and the flame sits at the stoichiometric conditions back again close to the lean side. We have intermediate markers like hydrogen peroxide and ketohydrogen peroxide that tell us our reaction progress variables, if you like, to show us the progress of ignition for these low temperature ignition phases. You'll see H2O2 and H2O and heat build up during low temperature ignition, and then you'll see their disappearance as hot ignition occurs. So I'd like to show you a movie that was rendered by Quan Lu Ma and his students, Chris Yi, Min Shi, and Fran Sar. And this shows the ignition delay in this simulation. And what you'll see on the left is a volume rendering in physical space showing the formation of the low temperature ignition cool flame kernels through the ketohydrogen peroxide species. And then overlaid on this volume rendering is the temperature ranges 1150 degrees Kelvin plus or minus a few to represent the hot temperature ignition front that forms sequentially after low temperature ignition. On the right side, you will see a cut plane of the hydrogen peroxide radical during ignition. So let me play it. So first, you see the formation of ketohydrogen peroxide, that's that low temperature radical soup due to first stage ignition. Started out on the lean side, the fuel's in the middle, it starts to populate the central part of the jet, and then it disappears as hot ignition, denoted by these orange structures at 1150 K. Start to populate the central core of the jet. And you can very clearly see the origin of this hot ignition without the clutter of all of the turbulence, which might obscure the hot products of combustion. So you can actually track these fronts for the hot ignition kernels by applying a distance function criterion. So I want to switch gears real quick just to illustrate that some of this volume rendering is very challenging, and we're also using it to look at scramjet combustion. These are cavity stabilized flames at high speeds and high compressibility. And what I'm showing here is a volume rendering, again by the same group, of the Enster turbulence field. And you can faintly see the lines for the cavity. It's a rectangular cavity here. And the corresponding heat release field. And on the right is the experiment, which shows a time-averaged luminosity, and this is the instantaneous rendered combustion rate. And so volume rendering is definitely useful, especially when we start to look at complex geometries associated with multiple blocks of data, and also eventually with adaptive mesh refinement. So I just want to point out some of the challenges with rendering at this extremely large scale. So to make these beautiful images and movies, as a scientist, we don't think it's a big deal, but in fact, there's a lot under the hood. And so rendering these multiple fields simultaneously requires a dedicated ray casting through the fields for multiple variables. We're always looking at causality between different chemical species and underlying turbulence and temperature. We have to be able to select features and that we want to bring out, and to do that we use opacity modulation using distance functions. So the distance, so that the 1150 Kelvin isosurface representing hot ignition, we can use a distance function to start to blur or resolve more coarsely as you move away from that front. And in that way, the turbulence and the mixing doesn't obscure the actual reaction front, which is the focus of the work. And then we want to use our knowledge about the physics to help guide the definition of meaningful transfer functions that are physics-based. Other issues, as I already pointed out, is dealing with complex geometries, nonlinear grid stretching, so we have to be able to handle sampling and interpolation distortions, low temperature resolution, temporal resolution, so if we don't save sufficient number of data restart files, we have to come up with clever ways to interpolate between the available time steps. And then just the vastness of the data presents challenges with how you manage the data, how do you move the data, and how do you do out-of-core rendering. So with this ignition problem and also with the earlier extinction problem that I talked about, one desire is to have a way to interrogate and query Lagrangian statistics in a post hoc manner. And to accelerate the querying of large amounts of data, we've come up with an in-situ approach, pre-processing approach that's done in situ to generate local probability density functions, or histograms, in relevant phase spaces for the scientists that can be used to guide and filter the interactive post hoc particle interrogation and statistical analysis. So in this work, we try to preserve the resolution and detail from the calculations for later post hoc analysis. And let's see. So we leverage the fact that we have all of the detailed time and spatially resolved information in situ. And so we can generate PDFs in situ that capture this information locally in smaller sampling regions. And then take advantage of these PDFs and resorting of the particles in the sampling regions following the decomposition of the PDFs. We can take advantage of that when we then later do post hoc feature exploration to make it faster and more efficient. So this is just an example of how we can use these PDF distribution functions as a data reduction tool that preserves the distributions. For example, the histograms of for example, the temperature mixture fraction fields. And the patterns that come up in these histograms, for example, a 1D or 2D histogram, are representative of the various physical phenomena that are occurring. As I showed you earlier when we did global statistics, we found that there are strong correlations with temperature with mixture fraction or the local mixing rate. So we can create histograms of both the field data as well as of the particle data while the run is ongoing. Then we make sure that the PDFs actually fit within the domain decomposition of the solver. So this is the global simulation domain, and the these subregions are the domain decomposition of the solver. And so what we do is we fit these sampling regions for the PDFs or histograms within the existing domain decomposition and not cut across several domains so that we minimize any kind of communication across domains. And so within each of these sampling regions, we can compute a number of histograms in whatever quantities you want to see them decomposed in. And then we also sort the particles that exist in those sampling regions and re-index them based on the decomposition of the PDFs. So this is an overview of what that workflow looks like. So the original workflow would have us compute the field data and the particles in situ, and then as a post hoc measure, we would have to load up all of the particles before we could query them and filter them, and then we'd do the analysis. So this is very expensive when you have large 50 million, 100 million particles. The modified workflow, as shown by these blue boxes, has us generating PDFs from the field data in situ and sorting the particles according to the PDF sampling regions, also done in situ. And then, as a post hoc measure, we can just read in perform the filtering then on the PDFs instead of on all of the data. You don't have to load all the particle data. So we do the filtering on the PDFs and load only those particles that are selected in the filtering of the PDF process. And this lets us load and analyze in a much quicker fashion without all of the overhead cost. And so this is just an example of what the interactive post hoc exploration tool looks like. It has 5 windows. There's the filter editor, then there's a particle view, and then these are orthogonal slice views that look at selected PDF regions in the domain. And then there's a zoom-in view where you look at detailed statistics. And, I should mention there's also a timeline view so you can see how the percentage of, how the PDFs in the sampled regions evolve in time. So we applied this to this large endodecane autoignition data set, which had 5 billion cells, 40 million particles, large case run on Titan with 120,000 compute processors, 7,500 GPUs, 500 terabytes of data. And so we were able to get examples of some of the PDF distributions between variables. In this case, the relevant variables to look at are the fuel-air mixture, this is the mixture fraction, and temperature, and depending on the frequency of occurrence of these bits of particles that sit in high temperature and where the fuel and air are properly mixed, those are the regions that will auto-ignite. And so we can then sort the particles in those regions and use them for post hoc analysis. The overall method scales well. There's very little overhead in terms of the generating the PDFs and storing them. I think the PDF uses only 5% of the particle storage. The PDF generation timing itself is small. It's only a fraction of the time that it costs to advance the simulation step. Also, the particle sorting time using an indexing method is also quite small. And so ultimately, what we find is that the amount of time to do the post hoc particle loading and selection is vastly reduced compared with loading all of the particles without this tool. Unless you get to a very substantial fraction of the data, if your features are really big, then there's some crossover point. But for the most part, we save a lot of time by using this approach. So I'd like to say a few words about back to the rich design space for workflows. We also looked at 2 different approaches of computing analysis, some of the key analysis on the same cores as the simulation, so this would be doing in situ, and these would execute synchronously with the simulation every maybe 400th or 20th time step, and it would share the memory of the simulation via a handoff copy. In a second modality, we also looked at doing some of the analytics in transit or hybrid in situ in transit on dedicated nodes on the same machine. This is done on Titan at scale. And these were then executed asynchronously where the data was moved off using a staging mechanism, this was Dart and data spaces, to dedicated nodes or external resources. So we combined 3 analysis methods, statistics, volume rendering, and topology with S3D. This is the DNS code. And we did this with static scheduling using MPI. And so with a lot of computer scientists reasoning about the workflow design as well as the algorithm design for those cases, the upshot is that we performed an empirical study to show that it is feasible to have these hybrid workflow architectures minimize the impact of the simulation. So these are just some performance numbers showing the cost of performing a calculation in situ in blue the data movement cost to stage off to a separate set of nodes in orange, and the in-transit cost if you were computing on a secondary stage set of nodes. And so when you look at the in-situ statistics and the visualization, these have minimal cost. These are units like a fraction of about 1/16 of the cost of a simulation time step. And so it's fine to keep most of those types of analysis and viz tools in situ on the same cores as the calculation. On the other hand, the topology methods, because they involve large graphs, traversing large graphs, had to be staged so that the construction of local merge trees is highly parallel and could be done in situ, whereas the final stitching together of these local trees to provide the global graph required an enormous amount of additional time, 120 seconds, which is far longer than the cost of a simulation time step. So by separating parts of the algorithm that scale well versus others that may require global aggregation and moving those off to other nodes or other compute resources, you can minimize the impact on the calculation. These scaling studies were performed on Titan on up to 5,000 cores and on a relatively large production simulation. So moving ahead, I think that we still have a lot of programming challenges with coming up with dynamically composable workflows for in-situ viz and analysis. We need to still find greater amounts of parallelism and be able to hide latencies beyond what is necessarily obvious to developers. And I believe that this is best done by finding functional task parallelism. And in-situ data analysis in viz is just one example, multiphysics is another, of challenges that are related to how do you compose software dynamically, and it's a broad problem for complex applications with complex workflows. So some of the immediate questions that come up are, if you're an application, who owns the data? Does the application own the data, or does the analytics own the data? Where's the data located? Where should it be? How is it represented? And then similarly, who owns which compute resources? Do I own the burst buffer, or do you, or which parts of memory? And when do I own that? And so to be able to reason about this and orchestrate this whole workflow, I believe requires a unified data-driven programming model for in-situ analysis and viz. And so a data-centric task-based approach might better understand the holistic workflow, since it has a high-level view of the data use and all of the dependencies. And so it can implicitly find more parallelism and flexibility in terms of how to schedule the various tasks, be them from the solver or from the analysis. So this would further separate the implementation of an algorithm for analysis or viz or library or the solver from how the application is actually mapped onto a machine, onto the different memory resources and processors. So the runtime system would allow us to analyze and allow mapping of a dynamic application workload. So one example of, and there are many of these data-centric task-based models, asynchronous task-based models out there, is Legion, which allows us to reason about data dependencies. In Legion, logical regions provide a description of the relations between the index spaces and the fields. They don't instantiate the data, but it has no implied placement or layout of data, and then these data can be partitioned into disjoint or aliased subregions. These regions can be recursively partitioned, for example, in an AMR code. And then the Legion program is a tree of tasks. The tasks are functions that have explicit region data requirements. So it might use a subregion or a disjoint region. And it also has awareness, a knowledge of the privileges, and whether it's a read-only, write-only, or various, how can it access the data. And so with that knowledge, it can execute the software with apparent sequential semantics, but it can also relax the order of the program order based on a data graph that lets it know dynamically about the data dependencies. And so in this way, the runtime can find implicit parallelism, both data parallelism as well as task parallelism, and it can hide latencies and do a much better job of it than if we were to manually try to code this complex set of dependencies between the solver and analytics. And so here's just one example of a S3D code that was rewritten in Legion with the help of the exact co-design team. The code ended up scaling much faster than the baseline production MPI code on out to about 2/3 of Titan, about 14,000 nodes. And this plots the weak scaling in terms of the throughput versus the number of nodes. And what you can see is at one node, we get about a 3x performance increase, and at large node counts, we get even a better performance increase of 7x due to the ability of the runtime to hide latencies across the network dynamically. And so using this as a tool, then we have included in-situ analysis of the chemical explosive mode, which is a eigenvalue solve on the reaction rate Jacobian. And the SEMA method, chemical explosive mode analysis, segments out local flame regions, which then, these black lines, based on the zero crossing of the eigenvalue, which can then be used to steer local grid refinement in an AMR sense. The problem is the SEMA, which is an eigenvalue solve, takes longer than a single explicit time step. And so dividing the analysis method across different Ranjikata stages and then interleaving it with other computations to hide the latencies would be very difficult to schedule manually. And so with the asynchronous Legion task model, we were able to schedule and actually run the code within about a day or two to implement this, rather than months. And so the performance of doing SEMA was measured then, actually measured without SEMA on the red, with SEMA on the blue in a production run on two different machines, Pisdane at ETH as well as Titan at Oak Ridge. And the cost of SEMA in the Fortran code was about half a second, about 1.2 seconds on Titan. And then doing it in Legion, allowed us to reduce the overhead by 84% on Titan and almost got the analysis for free on Legion. And so the runtime system really shined through here and allowed us to map dynamic application workload with, for SEMA. And so I think I need to stop here. So okay, so I'll just say, can I say two things in 30 seconds? Okay. So extending this work, we'd like to also find support for external resources in these tasking runtimes. Not only have the runtime see the holistic simulation, but also have it attach external resources for I/O, such as HDF5 files, Fortran record files, or key value databases to logical regions so that the Legion data model can see them and the tasks can operate on these external data like any other data that it already sees. And so the analysis of doing I/O with MPI/I/O at different data save frequencies is shown in the pink line, light pink. Doing it with Legion by itself is shown in the purple line as a fraction of the overall cost of a simulation time step. And the blue is this combined integrating the runtime with the runtime integration is the dark blue, which has a nearly constant cost and an insignificant fraction of the overall simulation time. And lastly, I think there's a lot of exciting research to be done in terms of embedded domain-specific languages for performance portability in the space of data analytics, so that we could write analysis tools and libraries as tasks with the data flow graph, and then using a runtime controller to separate out different runtime systems from these analysis libraries. And so I will stop here and say that it has been really fun working with you guys. I think a lot of the success has been due to the deep collaborations between domain and computer scientists. There's an enormously rich workflow design space for in-situ or hybrid in-situ and transit algorithms. And to get performance portability, I think looking ahead to future architecture designs, we really ought to move towards a unified data-centric task-based programming model together with embedded DSLs for analytics viz. So I will stop here.
So we have time for 1 or 2 questions. Are there any questions?
So thank you for a very interesting talk. You mentioned topology, but you have a non-steady flow. And so the critical points are going to be dependent on the coordinate system. Have you looked at a way of looking at a self-similar flow in which you actually can solve that problem?
I would like Valerio to answer that question.
So, yeah, now this we analyze this concept by concept, and we have now have much different technology
One more question.
Just Charles from Critical Friends. Just by curiosity, I would like to know which algorithm did you use for the merge-tree computation in parallel?
Which what?
Which algorithm did you use for the merge-tree computation during the in-situ visualization?
Merge tree. Well, I guess, again, this is Valerio and Timo's work. So like, my understanding is they do a local merge tree decomposition, and then if the features overlap are bigger than one domain size, then they have to do correction, join, and segmentation phase to aggregate the data in order to get a global tree. But they can probably express that way better than I can.
Thank you.
So, Jacquline and collaborators will be up at the podium for questions after for that. I mean, I think it was wonderful to have a domain scientist come and sort of talk about her issues, the issues of science and how it relates to data analysis. Let's thank the speaker again. And so this session is ended. I encourage you to come back to the SciViz, InfoViz, and VAS tracks, which start a little earlier. Please look at your program for location and time, because those sessions will start with an introduction after the lunch break. So thank you very much.